Every star is born from darkness, but not every star dies the same way. Some fade slowly, leaving behind a white dwarf. Others collapse with such unimaginable force that space and time surrender with them. From that collapse, something extraordinary is born. A place where gravity becomes almost absolute, where light is bent, time slows down, and matter disappears beyond a boundary from which nothing can return. In this journey, we will approach the event horizon. We will watch a star being torn apart. We will discover how black holes can launch jets across thousands of light years and influence the evolution of entire galaxies. We will examine the first real images of black hole shadows and the infrared signals detected by the James Webb Space Telescope at the center of our galaxy. And we will travel into the distant future, to a time when even black holes may finally disappear. Beyond the horizon, there is more than darkness. There is one of the greatest mysteries in the universe. Long before a black hole exists, there is a star. Stars are born inside enormous clouds of gas and dust. Gravity pulls this material together until pressure and temperature become high enough for nuclear fusion to begin. Hydrogen atoms combine to form helium, releasing the energy that allows a star to shine. For millions or even billions of years, a delicate balance controls its life. Gravity constantly tries to crush the star inward. At the same time, energy generated inside its core pushes outward. As long as these two forces remain balanced, the star survives. But every star has a limited supply of fuel. A star like our Sun will eventually expand into a red giant. It will release its outer layers and leave behind a white dwarf. Our Sun is not massive enough to become a black hole. The creation of a stellar black hole requires a much more massive star. Inside such a star, fusion produces progressively heavier elements. Hydrogen becomes helium. Helium helps create carbon and oxygen. Later stages produce elements such as neon, silicon, and eventually, iron. Iron changes everything. Fusing iron does not provide the star with useful energy. Once a sufficiently massive iron core forms, the star can no longer generate enough outward pressure to resist gravity. The balance is broken. In less than a second, the core begins to collapse. Matter is compressed to extraordinary densities. The outer layers fall inward and may rebound in a catastrophic supernova explosion. But if the remaining core is too massive to become a neutron star, no known force can stop its collapse. The core continues falling inward. A horizon forms around it. A new black hole has been born. In some cases, the star may explode dramatically. In others, much of it may collapse almost directly into the black hole, producing a weaker or even failed supernova. The details vary, but the final result is the same. A region of space has become permanently separated from the universe outside it. A black hole is not simply a giant hole in space. From a distance, its gravity behaves like the gravity of any other object with the same mass. If the Sun could somehow be replaced by a black hole of exactly one solar mass, Earth would not immediately be pulled inside. It would continue orbiting almost exactly as before. The danger begins when we move extremely close. The defining boundary of a black hole is called the event horizon. It is not a solid surface. There is no wall waiting there. It is a boundary in space-time. Once anything crosses it, every possible path through the future leads deeper inside. Escaping would require moving faster than light, which, according to our current understanding of physics, is impossible. For a non-rotating black hole, the size of this boundary is related directly to its mass. A black hole with the mass of the Sun would have an event horizon radius of only about 3 kilometers. A black hole 10 times more massive would have a radius of roughly 30 kilometers. The dark region seen in black hole images is usually called the shadow. The shadow appears larger than the event horizon because the black hole bends and captures the light passing near it. Just outside the shadow, some photons can travel around the black hole before finally escaping toward an observer. This produces a narrow and complex structure commonly associated with the photon ring. Behind the black hole, the universe appears distorted. Light from stars and from the far side of the accretion disk is bent around the black hole. This is why a flat disk can appear above and below the black hole shadow at the same time. We are not looking at a solid ring. We are seeing multiple paths taken by light through severely curved space-time. At the center, general relativity predicts a singularity, a region where density and curvature become infinite. But most physicists do not believe that the word infinite represents the final answer. Instead, it may show us where general relativity is no longer sufficient and where a future theory of quantum gravity is required. Black holes produce no light of their own, yet their surroundings can become some of the brightest places in the universe. Gas, dust, and even entire stars rarely fall directly inward. They usually carry sideways motion, known as angular momentum. Instead of falling immediately through the horizon, the material begins orbiting the black hole. It spreads into a rapidly rotating structure called an accretion disk. Within the disk, magnetic fields and turbulence transfer energy and angular momentum between different regions. Some material moves outward, other material slowly spirals inward. As the gas is compressed and accelerated, it heats to extreme temperatures. Around stellar mass black holes, the inner disk can become hot enough to radiate strongly in X-rays. The black hole remains dark, but the matter surrounding it can outshine entire stars. The disk may also appear brighter on one side. This is caused by material moving toward us at a significant fraction of the speed of light. Relativistic effects amplify its light, while material moving away from us appears dimmer. The result is not a perfectly symmetrical ring, but a dynamic and changing environment. Black holes do not behave like cosmic vacuum cleaners. They do not automatically consume everything around them. Most nearby matter can remain in orbit. To fall inward, it must lose enough energy and angular momentum. But once material reaches the final stable regions of the disk, its journey toward the horizon becomes almost inevitable. A star passing near a supermassive black hole may experience a much more violent fate. The side of the star closest to the black hole feels a stronger gravitational pull than the side farther away. This difference creates immense tidal forces. The star begins to stretch. Its structure is disrupted, and its material is pulled into a long stream of superheated gas. Astronomers call this a tidal disruption event. Not all of the destroyed star falls into the black hole. Some material can be thrown back into space. The rest continues along curved paths, colliding with other streams and gradually forming an accretion flow. As this debris heats up, it can produce a brilliant flare visible across enormous cosmic distances. For a short time, the destruction of a single star can make an otherwise quiet galactic center suddenly appear active. These events allow astronomers to discover black holes that would normally remain invisible. We do not observe the black hole directly. We observe what its gravity does to the matter around it. Black holes exist across an astonishing range of masses. Stellar mass black holes form from massive stars. Many contain between several and dozens of times the mass of the Sun. Some exist in binary systems, orbiting alongside a normal star. Gas can be pulled from the companion, forming a hot accretion disk and producing powerful X-ray emissions. Beyond them may be intermediate mass black holes, containing hundreds or thousands of solar masses. Evidence for this population is growing, although they are more difficult to identify. At the centers of most large galaxies, we find supermassive black holes. These objects contain millions or billions of times the mass of the Sun. At the heart of the Milky Way lies Sagittarius A star, a black hole with a mass of approximately 4 million suns. At the center of galaxy Messier 87 is M87 star, containing about 6.5 billion solar masses. A more massive black hole has a larger event horizon. Paradoxically, the tidal forces at the event horizon of a supermassive black hole can be weaker than those at the horizon of a small stellar black hole. an observer might cross the horizon of a sufficiently large black hole without immediately noticing a violent local change. But crossing the horizon would still make escape impossible. For most of history, black holes existed only as mathematical predictions. We could not see them directly. Instead, astronomers searched for their effects. They observed stars orbiting massive, invisible companions. They detected X-rays from superheated accretion disks. They measured stars moving at extraordinary speeds around an apparently empty point at the center of our galaxy. Those orbits revealed that millions of solar masses were concentrated inside an extremely small region. The best explanation was a supermassive black hole, Sagittarius A star. In 2015, scientists announced the first direct detection of gravitational waves from merging black holes. Two black holes had spiraled together and collided more than 1 billion years earlier. The final moments released energy through ripples in space-time. For the first time, humanity had not only detected black holes through light and moving matter, we had detected the vibration of space-time itself. Then, in 2019, the Event Horizon Telescope collaboration released the first image of a black hole shadow. The target was M87 star. The Event Horizon Telescope is not one traditional telescope. It combines radio observatories distributed across Earth, creating the equivalent resolution of a planet-sized instrument. The orange ring in the famous image is not the black hole itself. It represents radio emission from extremely hot material surrounding the dark shadow. In 2022, the collaboration revealed the first image of Sagittarius A star. Although it is much closer than M87 star, imaging it was more difficult. Gas around Sagittarius A star changes on timescales of minutes. During the observations, its appearance was constantly shifting. Scientists combined many possible reconstructions that matched the telescope data to produce the final averaged image. The James Webb Space Telescope has now observed infrared flickers and flares from the region around Sagittarius A star. The black hole itself remains dark. What Webb detects is changing infrared light produced by hot material moving through its immediate environment. The Chandra X-ray Observatory has also tracked changes in the enormous jet powered by M87 star. These are genuine astronomical observations, transformed into images and time-lapse sequences that allow human eyes to study processes occurring millions of light-years away. Imagine approaching a black hole. To a distant observer, your movement would appear to slow as you approach the event horizon. Your light would become increasingly redshifted and faint. You would not remain visibly frozen there forever. Eventually, your image would fade beyond detection. But from your own perspective, time would continue normally. You could cross the event horizon after a finite amount of personal time. For a sufficiently large black hole, the horizon itself might not appear as a physical boundary. There would be no sign, no wall, and no sudden flash announcing that escape had become impossible. Deeper inside, tidal forces would become increasingly powerful. Your feet could be pulled more strongly than your head. At the same time, your body would be compressed from the sides. This process is commonly called spaghettification. Near a stellar mass black hole, these tidal forces could destroy you before reaching the event horizon. Near a supermassive black hole, you might cross the horizon first and encounter destructive forces later. What happens near the predicted singularity remains unknown. General relativity tells us that collapse continues, but it cannot give us a complete quantum description of the final state. Black holes may hide the place where our two greatest theories, general relativity and quantum mechanics, must finally become one. There is currently no evidence that real black holes are portals, gateways, or traversable wormholes. Those ideas remain speculative. The real physics is already strange enough. Some feeding black holes launch narrow jets of plasma at speeds close to the speed of light. The jets do not emerge from inside the event horizon. They are created outside it, where rotating material and intense magnetic fields interact around the black hole. The rotation of the accretion system, and possibly the spin of the black hole itself, can help power and organize these enormous beams. In galaxies such as M87, a jet can extend for thousands of light years. It can heat surrounding gas, slow the formation of new stars, and influence the evolution of the entire galaxy. Black holes can also collide. When two orbiting black holes lose energy through gravitational waves, their orbit shrinks. They spiral together faster and faster until their horizons merge. The final black hole vibrates briefly, releasing gravitational waves in a pattern scientists call ringdown. The result is a larger black hole, but not one containing all the original mass. Some of that mass has been converted into energy and carried away through gravitational waves. For a fraction of a second, a black hole merger can release more power than all the stars in the observable universe combined. For a long time, black holes were believed to be completely eternal. But in the 1970s, Stephen Hawking showed that quantum effects near an event horizon should allow black holes to emit extremely weak thermal radiation. This is now called Hawking radiation. A black hole would gradually lose energy and mass. The smaller it becomes, the warmer it becomes, causing evaporation to accelerate. For black holes in the universe today, this effect is unbelievably weak. A stellar mass black hole is colder than the cosmic microwave background and currently absorbs more energy than it loses through Hawking radiation. Only after the universe has expanded and cooled for an unimaginable length of time would evaporation dominate. A black hole with roughly the mass of the Sun could require around 10 to the power of 67 years to evaporate. Supermassive black holes would survive vastly longer, potentially approaching timescales near 10 to the power of 100 years. These numbers are almost impossible to comprehend. The universe is currently only about 13.8 billion years old. Compared with the future lifetime of a black hole, the present universe has barely begun. As the final black holes lose their remaining mass, their evaporation should accelerate. But the exact final moment is uncertain because it requires a complete theory of quantum gravity. We do not yet know whether evaporation ends in a final burst, a stable remnant, or something physics has not yet revealed. Eventually, if the prediction is correct, even the last black holes will disappear. The universe will become darker, colder, and emptier than anything we can imagine today. A black hole is not simply the end of a star. It is a meeting point between gravity, time, quantum physics, and the evolution of the universe. It can be born in the collapse of a massive stellar core. It can tear apart stars, heat matter to millions of degrees, and launch jets across galaxies. It can collide with another black hole and shake the fabric of space-time. And after surviving for almost unimaginable cosmic ages, it may slowly fade through Hawking radiation. For generations, black holes existed only inside equations. Today, we have detected their collisions. We have watched stars orbit them. We have measured the light produced by matter at their edges, and we have created the first images of their shadows. But the greatest mystery remains hidden beyond the event horizon. There, our current understanding of physics reaches its limit. Perhaps one day, a deeper theory will explain what truly happens inside. Until then, black holes remain what they have always been, the darkest objects in the universe and some of the brightest windows into the laws of nature.